table in the book.
Oh, okay.
I remember that page I attached to my notes. I think there's 6 of them there. You probably want to give them.
Yeah, the ones in the notes.
Yeah.
Okay. And the other thing was, what was our homework due on Tuesday? The one where we had to write how to say keys based on function?
Yeah.
How does that work? Don't really see it in the
Traces.
traces.
Traces is the best way to do it.
But if we set one of them equal to a constant, we still have two.
That's right. So, for example, if say that c is equal to something times x times y or something, right?
Yeah.
If you said that c is equal to constant, then you can say something about how y and x are related. So that can tell you what on the xy plane what fraction is. So that's equivalent to
Oh,
looking
if
down.
where xy is 0, it always has to be 0.
Yeah, and that's the idea. So in 3 variables, set 1 of them and find out how the other 2 are related. And then try to piece together the different behaviors.
Okay. Thank you.
Okay, good morning. Okay, that was really, really bad. Good morning. Much better. I'm going to do calculus today, of course. So, we're still going to be using a lot of what you already know. And in 14.2, we'll be looking at limits. This might be the we're getting to the point where things in three-dimensional calculus will be different from two-dimensional by quite a bit. Right now, you're still going to see a lot of things that carry directly over, but pretty soon, things will start to look a bit different. So first of all, let's do a quick review of what you already know about one-variable functions. Much of what we're going to be doing in the next few minutes carry directly over. And then you'll see where having an extra variable makes things more complicated. So you remember that if we write limit x goes to a, f of x, and if we say that's equal to L, this means that as x gets closer to a, f of x gets closer to L. And that L is called the limit of the function f of x as x gets closer and closer to a. Now remember, when we say getting closer to a, we don't mean actually b at x is equal to a. Whether we could get there or not is entirely irrelevant. The fact that we could get infinitely close to a, that's the idea of the limit. On a graph, you can spot the limits very, very quickly. If the function is continuous. So here I got a continuous curve here. And you remember the idea on a graph, doing the limit means we follow that graph from both directions. And we get as close to a as we possibly can from both directions. And as we do that, we look at what happens to the y value. And for a continuous function, it's very, very obvious that the limit will be whatever the function is. But remember, even if the function doesn't exist at that point, here we have the same graph, but that point at x is equal to a is deleted. And in this case, you got to remember that taking the limit, letting x get close to a, means that we don't want x to be a. We want x to be as close to a as you can make it, and make it even closer. So x is equal to a does not mean x approaches a does not mean x is equal to a. If we could make x equal to a, that's great, but that's irrelevant as far as the limit is concerned. And you remember some of these classical examples of cases where the limit doesn't exist. like this one, for example. Right? From one side, we get closer and closer to, say that's 2. From the other side, we get closer and closer to -3. So we can't meet up, therefore the limit does not exist. You remember this stuff? Yep. Good. Looking at that first graph again on the previous page. The important thing here that we can take advantage of is that if f of x is continuous at x is equal to a, then the limit at as x approaches a is simply whatever f will be at a. So this is a case where we could get there, but when we talk about a limit, we're letting x get very close to a, and on a continuous graph, of course, that limit will be equal to what the function would actually give you. So this continuous part is a very important thing to know. And we can take great advantage of the continuous function properties when we deal with multiple variables. So let's make a list of functions that are continuous that we see often. Functions that are continuous on all real numbers for one variable function. Okay, so give me a few of these functions that you know. I'm sorry? X squared, okay, good. What about x cubed? What about x squared plus x cubed? What do we call that family of functions? Polynomials, good. Okay, good. What else? Sine and cosine, right. Sines and cosines. Sine and cosine. Not tangent. Tangent is not continuous at pi over 2, for example, right? What else? Exponential, good. And these are the ones that we see a lot. So keeping these things in mind will help you out greatly when you deal with limits, even in higher dimensions. We also see rational functions a lot. What are rational functions? Right, yeah, ratios of polynomial, right? Rational doesn't mean that the function is reasonable. It means it's a ratio of something. So yeah, these are ratios of polynomials. And rational functions are continuous on their domains. Whenever they're defined, they are continuous. And logarithmic functions are also the same thing. They're continuous on their domains. All right, so keep these things in mind as we deal with two-dimensional variables. Now let's start looking at the concept of a limit in 2 dimensions. When we deal with a 2-dimensional function here, when you talk about the limit, you're talking about letting x, y, this point, get closer and closer to some point that you want to define, a comma b. So now we deal with 2 variables changing at the same time, approaching one point, which is 2 numbers, simultaneously. So we write limit, and underneath that we write x comma y, approaching a comma b, of f of x, y. All right? So what this means is that if you look at the x and y plane, looking down on the projection of the surface onto the x and y plane, so imagine you got some kind of function that's 3-dimensional, and you want to know the limit at a point. The way to interpret this here, this means that we want the distance from some arbitrary point to the specified point to be very, very small. And when you talk about the distance here, we're talking about a small circle, basically. So imagine a tiny little circle around that point, a comma b. What we want to do is to bring a point, x comma y, into that circle, and we keep shrinking that circle. And simultaneously, we look at what happens to the value z. Want to be in this circle. And as that happens, we want to look at what happens to z. It's very, very similar to the idea of a one-variable function. In one-variable function, you only have one thing to control. You can only control the variable x. But here you got 2 things now, and it poses some problems for some of the functions that we'll see in a little bit. All right, so let's look at very simple examples first. Let's look at what happens to the function as x and y goes to 1, 2. And the function is 4x cubed minus 12x squared y squared. This is a classic example of a polynomial in 2 variables. You got x and y, 2 positive powers, integer powers, positive integer powers. So this is a polynomial in 2 variables. We know that it is continuous on all, for all possible x and y. continuous for all x and y. It's always defined, right? For every x and y, real number x and y you can choose, you'll get something out of it. You'll get a meaningful number, a real number. So it's defined for any x and y, any real x and y you can come up with. And you remember, if the function is continuous, the limit is simply equal to the function at the target, right? So knowing that the function is continuous, the limit is trivial, minus 44. This example is very similar. X and y go into 0, 0. E to the x squared plus y squared times cosine of xy. Okay, so we got the product of an exponential function which is continuous for all possible x and y. This is a cosine, and that's also continuous for all possible x and y. So that makes the entire thing, this is defined for any x and y, that's defined for any x and y. So the entire thing is also continuous for all possible x and y. Right? The product of two continuous functions is still a continuous function. We can't say the same thing about the ratio, but product, sum, difference, these are all continuous. So once again, taking advantage of the fact that the function is continuous, to find the limit, we simply substitute in the values. And we get a 1. Okay? So that's simple. Questions so far? Good. Let's check out this one. Let's make this 1, 0, and the function is natural log of 1 plus y squared over x squared plus xy. All right, so we got a natural log function. That function is something that's continuous on its domain. Okay, so in general, when is natural log of something defined? When that something is positive. Can that be 0? No, that something cannot be 0, right? So log is defined if, for this example here, 1 plus y squared over x squared plus xy to be strictly positive, but not 0. And now the question you want to ask is 1 plus y squared over x squared plus xy greater than 0 at the point 1, 0? If so, then we know we're talking about a part of that natural log function where the function is defined. Therefore, continuous, therefore the limit is equal to whatever the function is. And this is pretty easy to see, right? If I putting a 1 for x and 0 for y, yes. So therefore, natural log of 1 plus y squared over x squared plus xy is continuous at the point 1, 0. And therefore, the limit is equal to whatever that function is at 1, 0. And it turns out to be natural log of 1, right? Which is, what's natural log of 1? 0, good. So the limit is 0. All right, so in our last 3 examples, we're simply putting the point, very simply putting a point. Keep in mind, however, even though we substitute the point directly in, we are still not letting x and y being exactly equal to 1, 0, for example. We're letting them get really close to it. We did the substitution because we knew the function is continuous, and therefore it would be the limit. But in general, whenever we're dealing with limits, whether we could get there or not is completely irrelevant. What's relevant is that we could get really, really close to it and still get a meaningful number out of the function. Okay, now things get a little bit complicated when we're talking about a point that's not in the domain of the function. What if in the limit of this f of xy as xy goes to a and b, the point a and b is not in the domain of f of xy? Let's think back to the one variable calculus again, and we'll borrow the basis of that idea. You remember that in the one variable case, we want the one-sided limits. From the left and the right to be equal. Remember that? If they don't match up, then the limit doesn't exist. If they're different, the limit does not exist. In two-variable case, in a three-dimensional case, the fundamental idea is the same. But now we have a lot of different ways to get there. In a one-variable case, I can only approach from the right or the left, right? Think about a squirrel, two squirrels on the power line. If they are approaching the same point, there's no way for them to get around from each other if they don't go upside down and all that. But you see, they only have two choices, go front and back, left and right. No other choice. But if you talk about a plane, then you want to approach a point, you have a lot of different ways to get there. You can go from the east, the north, the southwest, south-southwest, go up and down and all that stuff. A lot of different ways to get there. In a two-variable case, so let me write that down here. In a one-variable case, we only have two ways to approach. In a two-variable case, remember the goal is that tiny little circle around that point AB. And we can get there by going this way, going this way, going this way, going that way, going this way, going along a parabola that way, and going along a sine wave that way. You get the idea, right? There's a ton of different ways to get there. How many ways are there to get to that place? Infinite, yeah, exactly. There are infinitely many paths to get there. But the idea is the same. Just like in the one-variable case, if the limit does exist, it shouldn't matter which way you get there. You should get the same number. Same thing here. It shouldn't matter which way you approach. You have to get the same number regardless of how you choose to approach. Right? Think of this classroom right here. We know the limit exists because we are here. It doesn't matter how you get here. You could take the gold loop, you could take the silver loop, you could walk here, you could bike here, you could, who knows, you could go to Lafayette and come back, right? The limit does exist because we are here. Same thing here. For that limit to exist, it really shouldn't matter which way you approach. So here's the key point. The limit exists if and only if the limit is the same from all directions. If you can find two directions that give you two different limits, then you can say the limit does not exist. Right? Okay, let's try this out. Limit as xy goes to 0, 0, y squared minus 4x squared over 2x squared plus y squared. We have a polynomial over a polynomial. This is a rational function. But 0, 0 is not in the domain. So we can't be certain that a limit will exist. There's nothing we can say until we actually check it out. So at this point, the answer is maybe, right? Until we check it out. So what we want to do here, think of this graphically what we're doing. Here's the target. We have to get the same number no matter how we approach. From all directions. What that means in practice is that if you can find two paths that give you different limits, then the conclusion is that the limit does not exist. If two paths yield different limits, then the limit does not exist. Does that make sense? Yes? All right. So looking at this picture here, what are two obvious paths to try first? There's two simple, very simple and obvious paths to think about. Yeah, along the x-axis, along the y-axis, right? So these are two obvious ones to try first. Let's look at the x-axis first, and then along the y-axis. If these two don't give me the same number, then the limit does not exist. End of story. If they give me the same number, then we got a little bit of extra things to work on. When we get there, we'll worry about that. Okay, so first let's try approaching along the x-axis. So that's right, this one right here. Along the x-axis means y is equal to 0. So therefore, the original limit becomes the limit. We're setting y to be 0 and letting x be free. So this reduces to a one-variable limit. Then we make y 0, so this is negative 4x squared on the top, and then 2x squared downstairs. Right? And what do we get? We get negative 2. So this is saying that if we approach along the x-axis, as we get closer and closer to the origin, the z level gets closer and closer to minus 2. Now let's try from the y-axis. Approaching along the y-axis means x is constrained to be 0, and y is allowed to be free, which we're going to take to 0 by taking limit. So the original limit becomes again another one-variable limit. We're constraining x to be 0. Y is allowed to be free, but going to 0. So now we have y squared minus 0, fixed 0, and downstairs is a fixed 0 plus y squared. Oh. Right? then what happens? We get a 1, right? So if I approach along the y-axis, I see 1. So think about the situation here where if you coming through the front and back door into this room, you're at 2 floors below the basement. But if you're coming along the right and left door, you're 1 floor up. So clearly, there's no limit here. You can't get to this place. You can't get to the same place by taking different paths. These are not the same. So the limit does not exist. Does that make sense? Yes? Any question on this example? Yeah. A graph of this, it would be, if you just look at 2 lines, then you have 1 line up here, 1 line down here. So we can probably graph what the rest of look like, but it'll look kind of like a cliff at this point. As you go here, you fall down. Kind of like 2 waterfalls put together kind of thing, right? You go here, and then down here, you're somewhere else. So there's some kind of very sharp rise or drop. Yeah. Yes. If we're going to x, y is equal to, let's say, 1, 2, then I wouldn't do that. I would fix my x to be whatever the target is, and then let y approach the target, but be free in general. Does that make sense? Okay. All right. Now let's see what happens if we get the same limits after the first 2 steps. You got to remember that if in the last example those 2 turn out to be the same, it is still not enough to guarantee that the limit exists. That means we checked 2 out of 10 trillion possible ways to get there. And we have 10 trillion minus 2 ways to check. So in practice, we can't obviously do that, but what do we need to do? And this example will illustrate that. And once again, I'm going to make the target 0, 0, just for simplicity. This in general would be whatever number that you wanted to go to. All right, so here we got x plus y times y minus y over x squared plus y squared. Obviously, 0, 0 is not in the domain of that function, right? So we'll follow the same procedure here. So first of all, 0, 0, not in domain. And if you plug in 0, 0 directly, you get 0 over 0. That you know from earlier calculus class means anything is possible. Okay, following the same procedure here, let's go along the x and y axis again. Along the x-axis means y is constrained to be 0, and we allow x to be free but go into 0. So this limit becomes this one, 0 up here, x squared downstairs. And what do we get? 0. Yeah. What about when x is exactly equal to 0? what happens? It's irrelevant, remember. X going to 0 means x gets close to 0, but not 0. As long as I don't make x exactly equal to 0, this will always be a 0. 0 over a finite number is forever 0. So just because it's going to 0 does not mean it is exactly equal to 0. Okay, we've got to keep that idea of a limit in mind here. All right, along the y-axis, this time x is constrained to be 0, and y is allowed to be free, but going to 0. So upstairs we get 1y minus y. Downstairs we get y squared. And same story here, we have 0 upstairs and a finite non-zero number downstairs. So this is still a 0. Okay, so we checked out 2 ways to get there. North and south, east and west, we get the same thing. Be very careful here. Just because these are the same, it does not mean the limit exists. We have to check a different path. In fact, we have to check infinitely many different paths. Technically, that's what we need to do. But, okay, let's try one more path and see where we end up. So this time, I'm going to approach along any non-vertical line. I want to approach along this line here. Y is equal to mx, where m is some number I don't want to specify. So in fact, if I can make y equal to mx work, it'll tell me all directions for any non-vertical line is going to work. And then I can worry about what happens next. So try along a non-vertical line, y is equal to mx. Let me first rewrite the original limit, and then we'll modify it. And now you let y equal to mx. And now you reduce that to a one-variable function, and still we want x to be free, but approaching 0. So this is limit x goes to 0, x plus 1 times mx minus mx over x squared plus m squared x squared. Okay, I simply change y to mx because that's the path I have chosen. I could have chosen x is equal to my if I wanted to, but it's the same idea. In fact, I could have chosen mx squared or cubed or something. It's just another path to check. If I simplify just a little bit, I get that. And as long as x is not exactly equal to 0, we can reduce those two things, and we end up getting m over m squared plus 1. All right, remember, all the one-sided limits have to be the same for the limit to exist. So now the question is m over m squared plus 1 equal to 0 in general? M is a real number you get to choose, the slope of the line, right? Is it equal to 0 in general? No, right, exactly. This is not equal to 0 in general. So this means that the limits don't match. And the limit does not exist. Okay, so that's the fundamental idea. They have to be the same number no matter how you get there. Okay, your question might be, okay, what happens if that turns out to be the same? Then you got to check a different shape. We check that lines work. Now we got to check parabolas. We got to check cubics. We got to check quartics and whatever fifth degree is called. And then we got to check cosinus. You get the idea, right? That is not something we can do in general. So let me give you one example here, what you would do. All right, so we're going to skip the first few attempts for this example. But let me just, after you check x-axis, y-axis, and mx, these all turn out to be the same. Same limits along x-axis, y-axis, y equal to mx. And what's next? Next, you got to check everything. Parabola, cubic, etc., right? Obviously, that's not something we can do. We can check all possible paths. When that happens, that's telling you that this is going to lead you nowhere. You're going to get all these things that are all the same, but each time you make one, you find out one path to be the same, it still doesn't improve your position. If you get one to be different, then you're great. But if you get they're all the same, it doesn't help you any. Go back and check out this function and see if there's something you can do to it. For example, could you factor stuff? And in this example, yes. Right? Upstairs is a difference of squares. We can always factor a difference of squares. So this is telling me that the limit of that function is equivalent to the limit of this simpler function. It does not mean that these two functions are equal. It means they have the same limit, but they don't have the same function value. And this is our good old polynomial. No, that's not how you spell it. Polynomial. It's defined everywhere. So I simply put in 0, 0, and I get a 0. And that's my limit, right? That is, because that's a continuous function, it's always defined, even at that point. And that has the same limit as that, even though that function is not defined there. This is just, they're the same shape with a hole taken away, with a hole at the 0, 0 location. All right, that's it. See you Friday.
We can approach with a logic
On this example, it will be all the same. If you approach along a line, a parabola, a cubic, you will all get zero. But
intuition, I think what really matters is the tangent line, the curve, the non-linear curve meets the point. That's what really matters.
and you're right that near the point, they look about the same, but the tangent line is never exactly equal to the point. Even though you can approximate.
What is the previous path method? You said we can approach something with a sine curve. Do you think the previous curve matters?
The previous doesn't matter. The fact that you have to check every possible path is what matters. I have to check a straight line. I have to check a non-vertical line. I have to check a parabola. I have to check a cubic.
Do you have a pen? This is the point that I would approach to find the limit of.
Yeah. So, okay, they look alike. Tangent line is alike. So at this point, if you zoom in, then you see this. But if you keep zooming in, they will never be the same.
You're telling me the results will be different.
It'll be different. It could be different. It could be different.
Oh, okay.
It could be different. Just because the tangent line closely approximate the curve of that doesn't mean they're equal.
So, is there a way if it's not on the domain of the function, if that point is not on the domain of the function, you have to change all the paths?
In principle, you have to, but in practice, you cannot. So you have to think of a clever way to avoid having to do that, such as factoring the function. Such as. You could also do a squeeze theorem sometimes. The book has an example using squeeze theorem. That's pretty neat.